Good, bad, different, like that, good. I don't want to make it too easy for things, but I want you to challenge you, get you to learn material. The midterm's in 2 weeks. The midterm will cover up to the end of essentially what we do this week, constraint satisfaction and stochastic local search. So it'll cover up to the end of that. Any questions? The midterm's not in 2 weeks. Is it? It's in 3 weeks. The election's in 2 weeks. The midterm's in 3 weeks. I typically did not have it on the same day. This is wrong. The midterm's in 3 weeks. Don't panic. Yeah, you freaked me out, huh? All right. I can't count, sorry. I can't count up to 3. All right. So what I've done so far is constraint satisfaction problems in times of variables, domains, and constraints. Okay. And we can solve them by search. We can search through the values for A, B for the variables. And then once we have violated a constraint, we can prune the search. Or we can use this sort of arc consistency. So an arc consistency is if for every value of x, it's consistent if for every value of x, there are values for the other variables that satisfy C. So essentially, if there's no value for x which satisfies the constraint for any values of the other ones, we're going to prune it because we can know that it doesn't work. And it can be used to simplify search spaces so that we can then solve algorithms more efficiently. Okay. Any questions about any of this? So all we're doing is arc consistency is just used to prune out values that we know are impossible. Okay, let's do. So let's just make sure. I have a few clicker questions here. I think it's the best way to learn, to work out what we know is to test our understanding of this. The domain of x is 1, 3, and 5. The domain of y is 2, 3, and 4. And the question is to make the arc between x and x minus y arc consistent, where that A does nothing because it's already arc consistent. B results in just 5 being removed from the domain of x. C results in 3 and 5 being removed from the domain of x. D results in 3 and 5 being removed from the domain of x and 2 and 3 removed from the domain of y. Or E results in 3 being removed from both domains. Remember the definition? How are we going? Anyone need more time? Anyone need more time? A couple of people. Anyone still need more time? Come on, 5, 4, 3, 2, 1, stop. Oh. Good. All right, good. I like these because I get to observe, as a teaching agent, I get to observe what people know and don't know. So 5 should be removed from the domain of x. So most people think that. But what about 3? Should 3 be removed from the domain of x? So is there a solution? Is there a possible solution given this where x is 3? Yes. Right? There is a possible solution for x where x is 3 and y is 4. So we can't rule out, just by knowing these 3 values, that x is 3. Okay? Does that make sense? So all we're doing is ruling out those. It's impossible for x to be 5. Right? So we agreed with that because that x is not less than 5. But it's not impossible that x is 3 because it could be that y is 4 as a solution. Okay, is everyone happy about that? So the answer here is B. Okay. This next one. Oh. It's exactly the same. Oh, no, it's not. So the domain of x is the domain of y are the same. We have the arc between y and x minus y. So now we're looking at the other the other arc. A, it does nothing because it's already arc consistent. B results in just 2 being removed from the domain of Y. C results in 2 and 3 being removed from the domain of Y. D results in the domain of Y becoming empty. Or E results in 3 being removed from each domain. Right over 140. How are we going? Do we need more time? Need more time? No, good, let's stop. All right, the answer is A. A few people said D. Results in domain of Y. So what we're trying to do is we're trying to say, is there an x such that y is bigger than x for each y? So so for y is 2, there is an x, namely 1. For y is 2, there's an x, namely 1. X is 1. And for y is 3, so for y is 4, x can also equal 1. So there is, for each value of y, there is an x that's bigger than it. So we can't prune anything. So the answer here is A. Does that make sense? Any questions? So everyone's clear now what we're trying to get here. So we're just trying to rule out those values that are impossible based on the other value. Okay, let's do. So again, this one should be easy. The domain of x is the same, but now we have the arc between x and x is not equal to y. So does it do nothing because it's already arc consistent? Does it result in just 3 being removed from the domain of x? Does it result in 1 and 5 being removed from the domain of x? Does it result in 1, 3, and 5 being removed from the domain of x? Or does it result in both domains being empty? Does anyone need more time? Okay, 3, 2, 1, I'm stopping. Hey, it's really quick when I do that. All right. Okay, let's see how does this. Oh. Oh. So why should 3 be removed from the domain of y? So why should 3 being removed from the domain of x, sorry? Is there a value for y that's not equal to 3? Yes. So there's 2 and 4. The answer here is A. You can't remove 3 from the domain of x because y could, as far as we know, we don't know which one y is going to eventually be. It's either going to be 2, 3, or 4. It might be 2, in which case we could remove, in which case all 3 of them are possible. It might be 3, in which case it's only 1 and 5, or it might be 4. So we don't know. We can't rule out 3. Okay? Does that make sense? We can't rule out 3 in the domain of x here. I thought that was a... Any questions about that? Yes? So what happens in the case where x and y? What happens in the case that x and y are equal? If we ever reduce the domain so that y is not no longer 2 and no longer 4, if we remove that so y has to be 3, then we can prune x as 3 from the domain of x. So if you removed x, somewhere else you removed x, y is 2, and you remove y is 4, then after that you can then remove 3 from it. So if you have 2 variables that just both have a non-empty domains and you have a not equals constraint for it, you can't prune either one. Right. Any other questions? Okay, let's go. So the crossword example. So the domain of one across is ant, big, bus, car, and has. and the domain of 2 down is ginger, search, symbol, and yogurt. And there's a constraint that says the third letter of 1 across is equal to the first letter of 2 down. Right, this is the constraint we did before. And we wanted to say after making 1 across C with that constraint arc consistent, the domain of 1 across is one of these. It's A is ant, big, bus, car, and has. B is big, bus, car, and has. C is big, bus, has. D is ant, big, car, and E is ant and car. Right, so just looking at how are we going? Do you need more time? Who needs more time? It was just a crossword puzzle. Haven't you done them before? Who doesn't know a crossword puzzle? Who's never seen one? All right. Phew. Okay, I think it's... Let's stop. We'll go 3, 2, 1. Let's stop. C. Yeah, it wasn't that hard, was it? Okay. It's just those letters that end in G, S, or Y. So any word, 3-letter words that end in G, S, and Y, we're considering everything else we're throwing away. Okay? And we want to do one more. Same question, same crossword puzzle, same domains. But now we're looking at the 2 down with C. So we've got the same words as before, but now we're looking at how we're going to prune 2 down. How are we going? Anyone need more time? No. Okay, 3, 2, 1. Oh, we're getting more. Okay, C. Ginger, search, and symbol. I'm sure that's right. Okay, any questions about that? It's just those, all it is those letters that end in T, G, S, or R. So if you look at 1 across, the third letter is either T, G, S, or R, and so any words in the 2 down that start with those. Okay, any questions about that? We're sort of happy with what's going on with arc consistency, what that means. We're just ruling out those values of which we know are impossible based on just looking at something locally. Okay. So now what we're going to do. So remember what we did before is we ended up clicking on all those arcs until we ended up being arc consistent, and there was nothing else can do it. So there are 3 outcomes with all that can be arc consistent. So what can happen? Actually, hang on, let's go to here. Actually, I'll do this one. Load. Oh, no, run this. So what are the outcomes in here? Can anyone tell me what sort of outcomes we get after we do for this some example like this? Let's give a different example. I think this one's good. So if we run something like this, and we end up with arc consistency, do all of the domains end up being empty? Do some of them remain full? What happens to the domains at the end of arc consistency? So if I do auto arc consistency, and I should speed it up. So if I keep running this, what could happen? So what happens here? How do you know there's a solution found? From looking at the graph, how do you know there's a solution found? Well, let's look at the other example here. How do you know? Sorry, yeah.
Every arc is consistent, and there's only one value per variable.
Right. So after arc consistencies, then there can be every domain can have size 1. In which case, what happens here? What happens like here, where every element has a domain 1? What happens?
All of them have size 1.
Hmm?
All of them have size 1.
Yes, every domain has size 1.
But we're also arc consistent.
Yes. Oh, this is after arc consistency. Okay. The question was after arc consistency is stopped, after the after arc consistency has halted. Right, so we've got everything as arc consistent. We've run this thing, we've pruned all the domains, right, and we've got everything as arc consistent, and every domain has size 1. What now happens? We found a solution, right? What else could happen? This doesn't always happen. What else happens sometimes?
Some domains have size 0.
All right, some domain has size 0. What? Some domains are empty. Then what happens? There's no solution, right? What else could happen? Right, there could be some domains have more than one element. And then what do we know? Sorry? Well, there might be multiple solutions. What else might happen? Well, we actually don't know. There may be multiple solutions, there may be no solutions. That doesn't follow either. Maybe multiple solutions. And there may be no solutions. We don't know, yes.
Do you know which one you'll end up with? Is it determined by the graph itself, or is it by the sequence of arcs that we visit?
It turns out we end up with exactly the same graph no matter which sequence of arcs we visit. So it's completely determined by the domain. Yes?
Some domains having more than one element, is it possible that there could be one solution?
Yes?
What if every domain has more than one element?
Yeah, you can make it so there's exactly one solution. There's ones obviously with no solution. Let's try and... Yeah, so if you have... right. So the domain of A is 1, 2, 3. The domain of B equals 1, 2, 4. And the domain of C is equal to 1, 3, 4. Or maybe this doesn't. I'm trying to get it so that there's only one. Each pairwise has a solution, but between each three of them it doesn't. But anyway, I can't. I'll post it. I'll think of a simple example. But if you have in here, if you have A is not equal to B, and oh, I can't think of one with exactly one solution.
What do you think pairwise consistency is a binary operation?
Yes, it's a binary operation. In fact, you can show that you can't do better than this. Arc consistency runs in polynomial time, but this is an NP-hard problem to determine whether there's exactly one solution. So we know that there's not a solution to it. Anyway, let's.
So getting a problem such as this to arc consistency takes polynomial time complexity, is that it?
Yes, there's only a finite number of operations you can do. Each time you're going to only reduce it by the number of elements of the domain independently of the size of n. So it's very local, and you can only ever reduce it by as many neighbors as you have. Okay, so it's actually didn't have slides on that. This is actually runs in polynomial time in the number of variables. All right. So what do we do if we have multiple solutions? Let's go this one again. So let's do arc consistency again. So what can we do here if we have multiple solutions? What did we do before? What's another method that we have for solving this problem? Sorry, what other solution method could we use? Yeah. Right, we could just search it, right? Like we did before. So what are we going to search? We'll pick a variable. Let's just split on A. Right, A is either true or, A is either 1 or 2. And what should we do here? Should we just keep searching again? What else could we do? When A is 1, what could we do? Yeah. Right, what we could do is we could make A as 1. And now the only thing that can go wrong is that B could be different. Right, we could run arc consistency again. And we find out that it's arc consistent again. So then we could split on B. There's either 2 or 3. Right, we can split on B as 2 or 3. And it's 2. And now we have to check that this is inconsistent and this is inconsistent. We're going to prune it. And we're going to split on C is 3 or 4. And there's a solution here and a solution here. Oh, let's do that. C is 3. Okay. There's a solution. We can backtrack. C is 4 as a solution. Now we're going to backtrack to this other element at this point here. And now we could run arc consistency again. What's going to happen if I click on this? C gets removed 3. So this is C is 4 as a solution. It's a solution. And now I'm going to backtrack again to be up at this point. What's going to happen to B? Yes?
What's the difference between what we're doing now and what we did last time with the trees and pruning? Because it looks like you're still expanding it and then just pruning where it wouldn't follow the rule.
Yes? So the question was, how is this different to the search that we did last time? And it looks very much like it, right? But what happens when I do this? What happened before? At this stage here, what would happen before? At this point here, we did lots of branching, right? At this point before, we were doing lots of branching for A is 2. But it turns out for when A is 2, we can solve what happens. We prune B, we can prune C, and we end up with one solution. So here we end up with A is 2, B is 3, and C is 4. So we ended up having a very much smaller search space than we did before. We had the branch on, we had extra branching factors on things. So let's do this other, let's do another one. I think the scheduling problem too is interesting. Except I want to do this. So let's move this around so we can see it. All right. This custom here is, let's explain this a little bit. This example here, this custom here is, I think it's A minus E is even or odd. So the custom here is A minus E is, what does it look like? Is it odd or even? Can anyone see? Odd. Okay. So constraint here is just, you can just represent it as a table. So when we have these other constraints that aren't built in here, we just write it as a table. And it turns out that if you actually run our consistency on this, you'll end up with a solution here that doesn't have, right, that doesn't prune every domain down. And if you want to find multiple solutions to this, we can start splitting on domains. Now you can imagine splitting on each of these, just doing search on this, but you'd still get a very complicated graph because there's still, 3 times 3 times 2 times 2 times 2. So there's 8, 9 eighths. There's still 72 sort of size of the tree that we potentially have to search here. But if you can split these into A, if you can split it into just the value of 1, let's do this one here. All right. So if we can split A is either 1 or 2. Right, so when we make A as 1, the only constraints that need to be checked are those ones that connect up to A. So we don't have to restart the search again. We can just re-look at these particular constraints. And now we can run our consistency again. Actually, I'll make this. So we can run our consistency again, and it's going to and we end up finding out that although there was lots of potential solutions in there, that everything else gets pruned down to just B is either 2 or 3 here. So we're going to split on B. It's either 2 or 3. All right, and then we can do auto arc consistency again, and it stops. So there's one solution. Okay, we can backtrack to this other solution to now B is 3, so we've got this next branch here. Sorry, B was either 2 or 3. So splitting up to the B is 3, we're going to run it again. And pretty quickly find out that there's another solution. And now we could backtrack again to this case about where A is 2. And we can run it again. And oh, don't know what's going to happen. Something will happen. All right. And we find out quickly that there's no solutions when A is 2. Okay, as soon as one of these domains becomes empty, then everything else sort of propagates out. Okay, so there's only 2 solutions to this problem. Okay, any questions about that? Yes? Hmm? 1, 2, 3 is a solution. Oh, I don't think I can make it so you can, sorry. No, it's 1, 2, 3 is a solution. There's actually all of those found were solutions. This one here, this branch here, ended up finding no solutions. So it got pruned. Any questions about that? Yes?
Why wasn't A equals 2 proved by our consistency? Why wasn't A equals 2 proved by our consistency if it yielded no solutions?
Oh, just because it's arc consistent doesn't mean there's no solutions. An obvious solution with this is for this. No. Just because it's arc consistent does not mean there is a solution. So if we have, I'll use this. If we have 1, 2, 1, 2, 1, 2, and we have A equals B, and A is not equal to C, and B is not equal to C, right? This is arc consistent. For every A, there's an element of B. For every B, there's an element of A. For every A, there's an element of C. For every C, there's an element of A. For every B, there's an element of C. But it's not arc consistent, right? So this is arc consistent, but there's no solution. We still have to search through these other cases. So in fact, we essentially know there's no algorithm that can run fast and guarantee to tell me whether there's a solution or not. It just does local information.
What if we change the constraints to A does not equal B, and A does not equal C, and B does not equal C? Would that still be arc consistent?
Ah, so you want the constraint to be A.
So a single constraint.
Hang on, A is not equal to C, this one. Is that arc consistent?
No.
Right, so this is not arc consistent. There is no value for B and C that makes this true, right? Because there's no values for B and C. For either of it, there's no value you can choose for B and C for A is 1 or for A is 2. Right? There's no value for B and C that you can be chosen for A is 1 or for A is 2. And if this was our arc, we'd prune both of them. Does that make sense? Yes?
Couldn't one argue that doing something like that is no better than just doing the initial search? Because the entire point of doing consistency is to reduce the domain. And if you're trying to put all your things into an AND statement into one thing, every domain is connected to one node. So it's no better than just searching.
Yes, there's a number of algorithms that people do that let you, there's something called 3 consistency and 4 consistency, which lets you put in not just arcs, but higher level orders of, not just pairs of things, but lets you put in constraints, and you can solve more and more of these things. It tends not to be used because it tends to be more What tends to be used is just using arc consistency because you can do it really fast and then searching. So you could do this. You could do arc consistency, and then you could start putting pairs of constraints in and all sorts of other things.
Right, but in this problem case, doing something like this, doing a method like this would not be better than just searching it without any arc consistency search at all. Like if you
Yes. Yes. Yeah. Yes, this doesn't, so you wouldn't do this. This is a, but you can do ones where you start off with small things and get bigger. Yes?
So in the case of having multiple domains within one element, would we get a set of different solutions if we started off with domain fitting a different domain than the one we just picked?
All right. So the question was, if you pick this in a different order, do you get a different answers, or do you get a different search space? Well, so that's a good question. Let's actually play with that. Let's do auto arc consistency on this, and we'll try and choose a different variable to split on first and see what happens. Because remember what happened in, is it stopped? Remember what happened when we did search. It greatly depended on the ordering of the variables that we chose. So let's stop here. Let's split another one. What should we split on? E. We're going to split on E. Split on 2. So we're going to split on E. So E was, oh, what was it? I forgot now. Oh, well, 2, 3, or 4. Now we've chosen, look at E is 2. We're going to run auto arc consistency again. We'll let this run to arc consistency, and we'll find that there's no solution for E is 2.
As it turns out, we have no way of comparing the graphs as we try to have a solution for
Oh, the solutions are going to be the same. There's only 2 solutions.
It will be the same. We can write them out, so we can't.
Oh, so you want me to run this again and write these things out? No. You can play with it. It's all online. Let's backtrack this. Let's do auto arc consistency again. And we'll find out that we hardly solved it at all. Oh, sorry, that was 3 or 4. Let's split on 3 again. So there we ran auto arc consistency with 3 or 4. We didn't prune anything. 3. And if we do it for 3, we'll find out that we find a solution, maybe? No, no solution. There's no solution here. And so now let's backtrack. So Z is 4. And now we have to split on B again. Turns out that if all of the domains have size 1 except one variable has domain of size 2, then we know there's 2 solutions, right? Because we can't prune either of those 2 values. So we know there's always a solution in this case. There's always 2 solutions. So we end up with 2 solutions here. Let's just do it. We can split on B as 2. Turns out it's not going to do anything. It only ever just does 2 arc consistency steps here. And we split on another one. Backtrack to B as 3. We have to resolve these arcs. Okay, questions? Yes?
Can we represent a constraint that involves more than
Yes?
How can we do that?
We just did it there. We just did it. We could have x plus y as z, for example, between 3 variables. And we have to work out for every, so we could have we'd have something like x plus y equals z. And here we have to check whether, here we have to check whether for every x there's a x, a y, and a z that satisfies this.
But in a diagram, how do we draw it?
Oh, I can't remember. There's add constraint in here. I think you can construct a constraint and you add it and you add arcs or something. You can do it. You just add it in and then this has the constraint on no variables. You can add variables to them. Any other questions? Yes?
Are there ways of understanding whether doing an arc, checking for our consistency before running a search algorithm is going to be more efficient than just simply running the search algorithm in the first place? So, given a constraint satisfaction problem of infinite size, is there a way of checking whether that constraint satisfaction problem we would do better in running it off and bringing it to our consistency than just searching through all of the possible outcomes?
So from lots and lots of experiments of people building systems, you invariably save by doing arc consistency before you do search. You prune it as much as you can. Every time you do it, instead of searching blindly, you prune as much as you can. And that turns out to be a huge win in these sort of problems. So prune as much as you can before you search, because exponential growth is going to kill you in the end. And this is trying to sort of reduce that branching factor as much as it can. Right, so here we're trying to reduce the branching factor as much as we can. So here we're trying to get much smaller search trees.
So pruning always takes point of time, whereas searching takes exponential time, and so would it always.
Yes, but the pruning it's not always the case, because this might be expensive and not prune anything. So if we have an example of assigning students to courses, and there's all of the rooms are possible, then it's very hard to start off with arc consistency doesn't prune anything, because everything's still possible until we start assigning things to values. And once we've assigned a few things to values, we want to prune everything else. Right? So it's often the case that we know a priori that that arc consistency won't help.
So the idea is go down a few steps in the tree and then start pruning from there, and then maybe do that for the next step.
Right, but what happens with arc consistency is that when we prune, remember when we did this, we only had to check very few extra constraints. So running arc consistency at the top means that when we assign a value, we only have to do very little extra work to do this. So if you remember doing this, let's reset this. I hope that, let's do, so if we run arc consistency on this again, you notice that if you remember the rule that we did is when we could, so we've done this, we've made this arc consistent, and now we're going to look at A let's do another one, let's do D. Split on D is 2. So when we split on D as 2, there's only 3 possible constraints that could have been violated. So instead of having to redo arc consistency from the start, we now have a much simpler problem where it's only locally, we just have to change things locally. And if arc consistency is useless, if it's not helping, if it doesn't prune any domains, we just stop straight away. So we know that if arc consistency is not pruning anything, it's very, very fast. Right? The only time we're going to propagate out is if arc consistency is actually doing something. So if it's useless, if it's not doing anything for us, then it's going to stop very quickly. So it has that nice property. Any other questions? Okay. All right, let's go back to here. I think we did all this. Let's look at here. So we did 3 outcomes when they're all consistent. One domain is empty, there's no solution. Each domain has a single value there's a unique solution, and when some domains have more than one value, there may or may not be a solution, we don't know. Okay? If some domains have more than one element, then we did search. And the domain splitting algorithm is essentially trivial. We split a domain, then recursively solve each half. Right, using exactly the same algorithm we did before. To recursively solve each half, we run arc consistency again, and then we do domain splitting if necessary. So that was the algorithm we did. Here we divided one element off in 2, but if something has a large domain, it's often useful just to split it in half rather than anything else, because we can split domains in half. We can do arbitrary things in splitting domains. And as we saw before, we don't need to restart arc consistency from scratch. Because remember the rule that said when we need to recheck arcs, we only need to recheck an arc if the other variables have changed. So only never need to recheck this arc if y and z has changed its value. Right? So we don't need to, once we've reduced the domain, we don't need to start that arc consistency from scratch. It depends what, in the level we're doing it doesn't. So it depends on how you actually go about checking these constraints. Because often you might want to split them in sorted order or not. Okay. All right, any other questions about that? So on Wednesday, we're going to talk about local search. We're going to have a whole different sort of set of algorithms for solving these sort of problems. So let's stop there. There are assignment zeros on the table.